All right. Hello again. Now that we're kind of familiar with Octave, the third part of this will show you a nice application for image processing. There's a few other things that we didn't really talk about, and that is the rank. The rank tells us, the rank of the matrix tells us the number of significant rows or columns that's important for the matrix. So if we take a look at our matrix A, let's go back to our matrix A. If we do the row reducing, then we're going to have two non-zero rows. So the rank of A is actually 2. Rank of A should be 2. And not surprising, the rank of A will have the same rank as your sigma matrix. So rank of S, if you remember what S was this the matrix with the singular value information. The rank of S is also the same as the rank of A, which is 2. Okay, so what's this useful for? Well, it's used for a lot of things. In particular, it's used for image processing, and we have an opportunity to take a look at that in action. And so we will do that by some code that was already written. I think I kind of wrote this code a while ago. And what we're going to do is in Octave, we're going to input a picture. Here is the code for the MATLAB commands that we're going to be using. And let's just walk through it real quick. So it's going to look for a picture. So I uploaded a picture here called profile.seq. or profile_seq.jpg. So if you do this, you want to make sure that you upload the picture properly. It's really just drag and drop into this page right here. And so that's the first command. It reads in the picture. ImRead is image read. And I'm going to put that into a variable called pic. Now, pic is going to be a huge file, depending on the pixels, the number of pixels, because the image is going to be by pixel. And furthermore, this pic variable is going to be whatever the size, let's say 1,000 by 1,000 matrix, but there are 3 levels of that. So it's actually a 3-dimensional matrix, 1,000 by 1,000 by 3. And the 3 refers to the RGB shading that they have. So to avoid the RGB shading of things, I'm going to convert this into grayscale, so we just have 1 matrix to deal with instead of 3. So I'm going to call my matrix I this RGB to gray of this picture that I just inputted in. So instead of 1,000 by 1,000 by 3, it'll just be 1,000 by 1,000, and then the numbers inside of those matrices will be how much grayscale are you putting on. And for each of those pixels, you'll have a certain darkness, and then you put them all together, you get that picture. ImShow shows this image, if you want to take a look at it. All right. So now that we have that, I'm going to change this into nicer numbers for the computer, for the program to deal with. So I'm going to image it into a double. So it's going to take a picture, format it as a matrix, and make each of those quantities into a double, which is a data structure in a lot of computer science that's going to be not an integer. Okay, now here's the big command, SVD. So we're going to take the singular value decomposition of that matrix, and then we're going to store it into U and S and V. So we did that in our previous video. And then we're going to take a look at the rank. So the rank of this would be whatever R is. Now, after you know what the rank is, you're going to not use up all of it. And this is what's cool about this image processing, is that the rank could be as much as like 500. And so having a rank of 500 means there's that much information that you're keeping in your program. Now, instead of making the rank all the way up to 500, and instead of making your matrix, your S matrix, into this huge matrix, whatever the size is going to be, you can just keep the more significant ones that are not close to zero. So if you do an SVD, a lot of them are going to get closer and closer to zero, and so it's going to have a lot of information. But if you just trim it to a good enough amount, you can still regenerate your picture. And so we're going to rewrite your S, your sigma, into a new singular value that does not have everything. So it will have the first n+1 columns all the way to the end, n+1 rows all the way to the end, and then everything else would be zero. Let me say that again. So you're going to create a new matrix where you're going to eliminate a whole bunch of the other singular values that are probably insignificant. So we're going to get rid of that. So we're going to use two commands for that. We're going to use two commands so that everything else will disappear. And then you're going to get a new matrix called D. You're going to regenerate it with the new singular value set of values. But we're going to still keep the same U and V matrices. And then we're going to show the original image, and then we're going to show the new image based on how many we got. So let's take a look at this and run it code by code. So this is our picture. So I'm reading the picture. I have a semicolon here that says I don't want to see the output. I'm just going to read the picture. If you want to see the output, PIC is the new variable, and you'll see that it says it's execute payload is too large. So this is a huge matrix. Let's figure out the size of this matrix. So it's 480 by 640. So this is the matrix size. And remember, there's three of them because there's an R and a G and a B. So if I convert that into grayscale, again, it suppresses it because I had a semicolon, but if I want to see I itself, I'll type capital I in here, and then I'll get this huge matrix that maybe I should have not done, but I'll take a look at the size of this. And now I see it's just 480 by 640. So there's no more RGB, it's just the grayscale. All right, and I could show this, show. If I look at the original one, pick, this is my original picture. And if I do show of my new matrix, it's now grayscale. So we have the original one, and now we have the grayscale. So those are my two pictures. Okay. Now I'm going to work with that. By the way, the IM is here. These are all whole numbers. I want to make them into a double so that I can work with it properly. And so, again, IM double just means, let's take a look at I2. I2 now is a matrix full of doubles that's just going to go from 0 to 1. And 0 to 1 will, figure out for each pixel how deep it's going to be. Now let's do the SVD command. So SVD of this new matrix. Let's take a look at S. Well, S. See, there's a lot of zeros here, but what is interesting is to take a look at the first few numbers. The first few numbers look like it's a little bit of a mess too. Maybe we'll just do SVD I2. So these are the singular values associated with A. Now, if I look at it, I have 3.6 times 10 to the second power. So that's like, I think we'll move this 2 decimal places to the right. So 362. And then I have 52.723. And by the time we get to here, this is about a this is exactly 9.18. And then if I start scrolling down, I get closer and closer to 0. And at some point, I have 9.9 times 10 to the negative 1. So this is really 0.997. And then if I keep going, I have 0.45. So these are close to 0. And whenever your singular values get closer and closer to 0, they become insignificant. And so we go as far as 0.00995. And so those small numbers are really not that important. So what we can do is we can throw away about half of these numbers. We can figure out how many numbers there are, by the way, by the rank. So we take the rank of S. It looks like there's going to be 480 singular values. So that's about the size of the matrix that we had. So what we can do is we can create, instead of looking at that, we can create a new matrix where the size is not going to be 480. So if we create a new matrix that has a size of 50, for example, let's see, this is going to be our new matrix creation here. S is going to be we're calling it S2. S2 is going to equal to S. So I'm just going to copy that. And then I'm going to put this command. There's 2 commands that are happening here where I wipe out everything else. Other than up to 50, I think we're letting it n equal to 50. So let's change n into 50. And we'll run it. And let's find S2. S2 still has a bunch of zeros. But the first 50 rows will have the first 50. Here are the first 50 rows. Well, it's hard to see the first 50 rows like this. But then our rank is now not going all the way to 480, but instead it just goes up to 50. And then if I look at it side by side, the plots, see if I could do this. Oops, my second plot didn't happen. Oh, because I don't know what n is. I didn't really define n. So let's define n equals 50. And then run that command again. Nope, that didn't happen either. Oh, because S2. All right. So what I'll do is I'll just run this command or run this program. So this is my original, and this is my n is equal to 50. You see that they're exactly the same, but what I did was I disregarded out of the 480 out of the 480 singular values, I just kept 50 of them, and then I got this subplot. Now, if I take this to the extreme and maybe just kept 2 singular values and try to recreate this picture, I'm not going to have enough information. So I'm going to go ahead and run this with 2 singular values. and I'll see that I get a picture that looks like this, and that clearly is not like the original, not anything like the original. So if I scale this up and kept 10 singular values, so save and run, I have a slightly better picture than I had before, but it's still, this is, it's still not that good. So if I maybe kept 25, and I ran that, it's still a little bit blurry, but it's definitely improving and looking a lot better than what we had before. So the one where we had 50 looked like it was the exact same picture. So if I keep 50 of my singular values instead of 480, then I will get a result that is just as good as the original. So the result is just as good as the original, and I didn't have to keep all those 480 values. All right, so this is our program, and I would like for you to try to experiment with this. I'll have the code available, and then you can mess around with it in your computer. All right, good luck. Hope you had fun.